Antarctica contains between 60 and 90% of the world's fresh water in the form of ice. It may look relatively barren, but don't let its seemingly uniform appearance on top fool you. A dead satellite has now given us clues that something very interesting is hiding underneath. The satellite in question is called the Gravity Field and Steady State Ocean Circulation Explorer, pronounced GOCE for short because the European Space Agency is cosmopolitan like that. This slick little sports car of satellite was created to measure and record fluctuations in the Earth's gravitational field and global mean sea level. We then use this data to produce a model of the Earth called the geoid. Hold that thought, we'll come back to that in a second. The GOCE satellite completed its mission in 2013, but research teams all over the world have still been piecing together the data ever since its cute little butt burned up in the Earth's atmosphere. Because here's the thing about gravitational field data. It tells us what the Earth is like, even the parts of it we can't see. And here's where the geoid comes back in. The geoid is a hypothetical ocean. No tides, no waves, no nothing. In this model, the only things the world's oceans are influenced by are the Earth's gravity and the rotation of the Earth. Since objects with more mass have more gravity, the water of the geoid bunches up in places on Earth where there's greater mass, giving us a model of the Earth that looks a little bit like a misshapen ball. Its funky shape is our map to all the topographical features on Earth. So GOCE's mission was really important. The geoid lets us better understand ocean currents, sea level rise, and changes in ice coverage, but it also lets us see inside the Earth. Using 3 pairs of ultra-sensitive accelerometers mounted orthogonally to create what's called a gradiometer, GOCE took measurements that allowed one research team to calculate gravity gradients, which allow us to see the size and character of all the Earth's topography, including what's under Antarctica, the least understood of all the continents. Turns out, it's a patchwork continent made up of at least 3 different cratons, which are remnant rocky cores of long-lost ancient landmasses. And get this, each craton has geologic similarities to an existing landmass we know and love today. One is similar to Australia, one matches up to India, and so on. Now we finally know that this, Antarctica, is the accumulation of what was left over after supercontinent Gondwana broke up and all the pieces went their separate ways 160 million years ago. This new understanding of the tectonic puzzle pieces locked together at the bottom of the globe can help us visualize the plate tectonics of Earth past. How did the continental plates move around? What did they bump into? What mountain ranges and volcanoes and oceans did they create? But how does knowing what's under Antarctica's icy face add to the science of the present? Well, the ice is melting. Antarctica's ice sheets and glaciers are losing just shy of 300 billion tons of ice per year. And that's compared to the 1980s when the continent was losing just 44 billion tons a year. When factoring in melting from other huge ice sheets like Greenland, Antarctica's melting ice could contribute to up to 6 feet of sea level rise before the end of the century. Plus, we're contending with something called post-glacial rebound. Turns out the Earth's crust is pretty elastic, and after all of that heavy ice is gone off Antarctica's back, that landmass, all that bedrock, is gonna spring back up. Yeah, so it would be nice to be prepared for how that might play out. This most recent study, with the help of the handy-dandy GOCE data, gives us a detailed look at the rock composition and the configuration of landmasses underneath all that ice. The nature of the rock, the way it's all put together, and the way it moves will influence how fast the ice melts, what directions that water is likely to go in, and how the ice may shift as it melts and breaks apart. And remember, these are big freaking ice sheets, so knowing how they may move is pretty important. Collecting and analyzing data like this may complete our picture of how Earth changed and molded itself during formative periods of geologic time, helping us understand both its past and prepare us for its uncertain but definitely